Well, welcome everyone to Living Web Farms webinar. My name is Richard Freudenberger. I coordinate the energy and resource things here at the farm, among other things. So today we're going to talk about small-scale water distillation. And I'll be honest, originally when we were planning out some of these webinars, I had originally thought we'd stick with solar distillation, but after some additional research and looking at some economics and just the water quality and the and practically the speed, especially of the solar distillation, I've expanded the entire conversation to include not just solar things, but also other stovetop and other heated ways from energy of possibly gas, electricity, charcoal, anything else, to condition the water to get it to a distillation point. So this is going to be a nice small-scale water distillation discussion that is easily accessible to anyone, and I want to make sure everyone understands that, and it's not really an expensive proposition either. It's actually a fairly inexpensive thing, and even some household appliances or utensils would suffice for most of this stuff. So we'll go through all that, and I have some things to show you and some little video clips and whatever. So we'll start with the basics. So how would we use distilled water? Well, for most people, it's going to be drinking water, to produce drinking water that's free of minerals and contaminants. Actually, a little later on, we'll talk about why that may not be the perfect thing, or an absolute level of being free of minerals and contaminants isn't necessarily necessary. But that's probably going to be the reason that most people want to make their own distilled water. And that would be especially for areas where the water may be questionable. You really don't know what's in it, or it's possibly saline or brackish, salt water, dirty water, muddy water. Chemical water that is chemically impacted is probably not a good source to get water from in the first place. So we'll talk a little bit about that when we talk about filtration and separation. But other than that, you might want distilled water for a neti pot. If anybody's used a sinus cleansing neti pot, where you basically wash your nasal cavities with water to sort of flush them out and keep healthy condition in your sinuses. A lot of people like to use clear or cleaner water with less minerals in coffee makers. It's not necessarily because it makes the coffee taste better, although some people claim it may, but it's also to keep the coffee maker free of the mineral deposits that can build up and be a problem over time. Steam irons, that's a coffee maker you can clean fairly easily, but a steam iron is pretty difficult to clean without flushing it through. The passages in the iron are sort of small and difficult to get to. So you might want to use more of a distilled water in there. CPAP machines and humidifiers, again, for mineral buildup, to prevent mineral buildup. They actually sell CPAP water in the stores to put in those machines. Some people stand by using distilled water for shampoos and hair care products. In the automotive industry, batteries, flooded cell batteries, a typical car battery with the flooded cell construction, they require mineral-free distilled water. And cooling systems, a lot of people don't realize this. In the old days, when everything was iron, cast iron, cylinder heads, the blocks of the engines were cast iron, it didn't make as much difference. But now we have highly sophisticated alloys and aluminum and titanium and other things in the cylinder heads and in the blocks of the engines that are very sensitive to mineral buildup. So many, well, I would say probably all modern cars and when I say modern, I'm referring to something from the 1980s up to present, would do much better with distilled water in the systems. Medical procedures like kidney dialysis and things like that, they would require a clean distilled water for lacking of minerals in it. And laboratory testing and research, purity is important there. So of course that would be another area. But for most of us, the first few are where it's going to be applied. So we want that. The characteristics of distilled water is that it lacks electrolytes, potassium, other minerals, which have the ability to conduct ions, which essentially occurs when rainwater comes through the atmosphere and hits the soil. It filters down through the soil, and on the way through to become groundwater, as it passes through the soil, it naturally collects minerals. And there's a host of minerals, iron, calcium, magnesium, potassium. There's just a lot of things. I'll just show you in a little bit a water test result that I had from my private well, and you can see some of the minerals they test for and some of the parameters they look at when you pay for the test. Distilled water lacks electrolytes. Distilled water lacks sodium, and that's why it tastes flat. Now, in some cases, for health reasons, a low amount of sodium or a absence of sodium may be a good thing. For most people, a little bit of sodium is actually a good taste improver. So we might want a little bit in there, but distilled water just doesn't have it. Water low in calcium and magnesium has been linked in some studies to fatigue and muscle cramps. That's not a absolute, and it's not a deal breaker. I'm just mentioning that because that's a fact. Drinking distilled water exclusively, meaning if you cook and have a complete diet of distilled water, it can leach minerals from the teeth. However, with all that being said, we receive most of the majority of our mineral nutrients and salts do not come from our water supply, but they come from our food and supplements we might take. So any lack of salt or minerals that some advocates may say we need in our system are going to be replenished or supplied from food and supplements anyway. So that's pretty much the argument that I'm presenting. So there's a difference between filtered water, purified water, and distilled water. Filtered water is a simple carbon filter. I have one right here, the kind you might purchase, at home hardware store or home improvement stores, whatever, for your pitcher water filters. Very similar to that. It's just activated charcoal. Some of them have more. Some of them have other things in it that compound the filtration. But just the basic filtered charcoal filters will remove chlorine, and they definitely improve taste and will remove odors. As you buy the multi-stage filters or the compounded filters, again, for either pitcher pour filters or for your in-house or sink filtration systems, they can further remove things like lead and mercury and whatever. I don't want to say that lead and mercury are not important, because you certainly don't want them in your drinking water, but for the most part, and discoverable by a test, for the most part, most water does not contain like high levels of lead or mercury. However, it could. So testing is important, and we'll talk about that in a little bit. So what I said was activated carbon particles will bond to the contaminants, and the pure water will pass through. So the activated charcoal is basically, it's a fine powder, very, very fine powder, and I've just got a little bag of it here, granulated, very, very fine. And actually, it doesn't stain. You would think it'd leave big black marks that you have to wash out, but it's really not sticky like that. By the way, activated charcoal becomes activated by heating it, heating charcoal to a extremely high temperature. I think it's probably around 1700 degrees, and it creates air pockets and cavities within the charcoal structure. So it's then called activated. So that's filtered water. Purified water is mechanically filtered and processed to remove the chemicals and impurities. They actually go through several stages of and levels, like in municipal systems, that will do some heavy filtration, then finer, and then extra fine, and taste improvements, whatever. And of course, the testing goes on in real time, so that as water comes in to be processed, it's not contaminated with something critically horrible. So they can monitor that and divert it if necessary. So bacteria, chemicals, and any other contaminants are removed. And distilled water, as I said, is it's a type of purified water, but it's processed so that it really just removes, it just extracts only the pure water and condenses it, leaving everything else behind, and we extract and condense and use the distillate part of it. So in combination with, you can certainly just drink the distilled water, but if it is then passed through a simple activated carbon filter, then you can remove additional components that the distillation may not have removed, and you'll have water that is probably about 98% pure, roughly. I'm not going to say 100%, and some you may see advertisements or discussions for some certain home products that say 100% filtration, but I don't think it's a safe bet to say that. I say 98+%, and that's certainly more than adequate. I'm just going to go real quickly through the home water purification methods. We already talked about the carbon filters. Carbon filters will remove chlorine, and they definitely improve the taste and remove odors. And then additionally, the multi-stage ones can remove the lead and mercury and maybe some other things. But that's a physical carbon filter. The next step is a reverse osmosis system. It's actually a system that's plumbed into the house that takes in raw water, and it's a very effective way to purify water. It filters out, pretty much, it's such a fine filter that it purifies anything larger than a simple water molecule. But two of the things, drawbacks of an RO system, reverse osmosis, is that they do use a lot of water. I mean, they bring in 100%. So of the 100% of the water that enters the RO system, 75 to 80% is flushed away or discarded as contaminated. So you're getting really only about 20% of what you put into it, which is that's sort of a waste of water in a sense. And it also, the buildup of the remainder can be a problem, because what you're then discarding is it's fairly contaminated. But certainly no more contaminated than the water that came in. However, it's condensed, so it's contaminated in a large concentration. So that's always something to think about. And the systems are also a maintenance. I wouldn't say a problem. They're certainly not a maintenance problem, but there is maintenance involved. They have to be on a scheduled maintenance, and of course they cost money to purchase, plumb in, and then also to maintain. Ion exchange filters are used oftenly. You see I didn't have a picture of one, but they're usually tall, narrow cylinders that have a meter gauge at the top, and what they're basically hard water processors that that will strip out calcium and magnesium and to some extent iron. It cleanses the water and gives a good, better sense of taste, and replaces the calcium and magnesium essentially with sodium or salt, which is, another thought. In extreme circumstances, people who are on a very low salt diet or just really can't tolerate a lot of salt in their food or water, it would not be. There's other processes beyond that to strip the salt out as well, but you should be aware that the ion exchange filtration or hard water filtration does deliver water with a sodium content. And again, they have to be purchased and they have to be maintained. There's a zeolite or other type of content in there that attracts the magnesium and the calcium and builds up over time. That builds up and that has to be flushed out and the process continued. So municipal water treatment. I just threw this in here because I want people to realize it. Other than well water, I don't know how many people, what the percentage of the population in the United States anyway has, or North America has municipal treated community type water as opposed to private well water, but a large amount. So the municipal system is not going to allow in a lot of horribly toxic things. It's obviously there to help clean up the water and make sure we don't get toxins and bacteria in our water supply. And admittedly, sometimes systems fail, sometimes they aren't maintained properly, or sometimes they let some through and then they catch it and they'll fix it immediately and issue a statement saying that there's a problem with the water supply, and you have to flush it, or you have to let it run for a while, or don't drink it for 48 hours or whatever. But the city and municipalities try to do their best to keep it public health process. So there's a coagulation and flocculation process, which we don't need to really know all this stuff, but there's charged chemicals that are added to the water to bind with negatively charged particles, and it forms little clumps of material called flock, and this flock settles to the bottom of the container that the water supply is being processed in. These are huge, of course. And then the water is extracted from the top of the container above the flock accumulation at the bottom, and that water is a lot cleaner, of course, because it's been all the bad stuff has been removed. So they pull it out of the top of the supply and then pass it through various filtration systems in stages from large to small. So you get gravel, sand, charcoal, and it removes all the other contaminants that are either particulates or chemicals and viruses on its way through the processing. And then chemical disinfectants such as chlorine, we have our chlorinated water, is added to the system in safe amounts to kill any remaining bacteria, and then the water is passed on as safe and drinkable. So that's our municipal treatment. We do not have municipal treatment obviously in private well systems or in community private well systems. Sometimes you have a neighborhood well system that may be a couple neighbors get together and share a well. These should be tested on a regular basis to make sure nothing's gotten into the water supply. Well, unfortunately, we really can't see that very well. Okay, we're having a little. That's my fault. Oh, here we are. Okay. It's still a little small, but this is basically, I have a private system at the house. Every 5 years or so, I get a test. The testing is about, I guess it started many years ago. I think I paid $60. Then it was $90. Then it was $120. And now I think this costs me around $200. But I mean, it's worth it. One of the reasons I don't get it tested every year, but it's definitely something that should be done probably every 5 years, at least 5 years. And essentially, they will ship you a. There's this particular testing firm is one of many, so I'm not promoting this particular one. That's just what I have. They will ship you in a courier package a vial or two in a insulated box with prepaid labels and all this stuff ready to go, and then by a certain regimen of testing that they instruct you with, you turn your tap on and you take your test as close to the well supply as you can, and let the water run, and they give you a couple of parameters, do this, do that, and you fill the containers up, seal them tightly, put them back in the insulated box. The water has to be kept coolish to be tested correctly. So they're put in the box, and then you're supposed to bring it back to the courier service and to have it delivered back to the laboratory within 6 or 8 hours, I think, something like that. So basically, they give you a report, and it's based on standards, primary standards, secondary standards, any action levels that you might have to take, and then a little key here. They give you the ND is not detectable. The check is just, basically okay. Little triangles of warning, and you can see all the other things. And the next page will show you the, let me see, things like iron. That's okay. Okay, it's a little bigger here.
Adjust it.
Hold on, give me 1 second. Okay, we'll get it. Iron and things like pH, which is your acid alkaline measurements, iron, coliform, some other things are just really not as critical. Well, coliform is certainly is critical, but that's sort of a go no go. So PA means present or absent. That top line total. Well, I probably can't. I can't point at this point because it's been enlarged. But the yellow triangle in the upper left hand is the coliform test. And in some tests they give you, in some companies they give you they actually give you maybe a number. But in this case it's just saying coliform is present, and E. coli, which is more dangerous than coliform, is absent. So basically, there's just letting you know that you do have some level of coliform, which I'm sure almost every well supply, unless you treat your water beyond just coming out of the pipe, is going to have. And E. coli is absent in this test, which is great because we don't have any bacteria like that in the water supply, and there shouldn't be. Everything else, ND means non-detectable. So manganese, mercury, see, ND and mercury is great because you don't want a level of mercury. Nickel, potassium, selenium, silver is not detectable, uranium isn't, zinc is within limits, and the secondary levels, it's not really a critical measurement, so they're not giving you a warning on it. The testing comes with a detailed description of what all this stuff means. What the levels, with numbers, what the levels are. The first column shows you what your results were. The second column shows you the measurement parameters, milligrams per liter, or whatever else it might be. Then the next one, I believe, shows the government standards, like what it has to hit before they issue a warning, or before you are told it's too high. And again, the report includes a description of all this stuff, and then gives you some discussion on what to do if you have achieved dangerous levels or warning levels in any particular thing. So this is if you're concerned about your water, or as you should be. I mean, if you've bought a new house, or you moved into a new place, or whatever, and especially if you do not have city water or municipal water, it would be a good idea to invest the $200 or whatever it may take in a water test. Now, your county health department will do a basic test for you. Essentially, that's for coliform and E. coli and maybe some other things. but it will behoove you to go beyond that. And it may not be, there are very different levels of testing that you can get. So the one I get is usually in the middle. Sometimes there are tests that are given in agricultural areas specifically for chemicals through the groundwater, and in areas that might have heavy factory concentrations. There are volatile chemical testings that can be done specifically. So you can, the company you research for your test, or and eventually take the test from, will give you the available tests that you should consider, and they'll explain what you may or may not need. So distillation, now onto the topic of what we're really supposed to be talking about here. Distillation is essentially heating water till it vaporizes, and then condensing the water by cooling so the vapors return back to liquid, and what comes out of the liquid is, or out of the process, is a liquid that has been distilled and hopefully purified. Distillation is something that's been used for almost 2,000 years. Generally, from what I understand, it had been initially used boiling seawater to make drinking water. So what was left was salt and saline water, and what came out was water that was free of salts and sterilized because it had been boiled. It has been going on here for a long time. So that's the whole process, even though it's changed quite a bit since those times, is essentially very same. So how it works is that water has a boiling point that is lower than most of the contaminants and minerals in the water that you're boiling. So when you boil the water, the water turns to vapor or steam and is extracted through a condenser that looks something like this. This is a copper one I use for other things, but they can be all sizes. It's just a small one, but they can be of a thicker tube or much bigger. This one only has about 10 coils, but they go much more than that. So that's what it goes through on the way out. So since the water in the container it may have minerals, it may have toxins, it may have other compounds in there. Most of that stuff does not boil. The water has a lower boiling point than most of that stuff. So when you turn the heat on and you get that water vaporized and then essentially boiling, it will the purest water will vaporize and leave the system, and what's left in the container or the bucket or the vessel is the contaminated water. So that's essentially it in a nutshell. Water distillation is the simplest form of many other types of distillation we use in chemical and the beverage industry. It's the same process they use to make ethanol or ethyl alcohol. It's the same process they use actually to vaporize to what they call crack crude oil to make diesel fuel and gasoline and every other alcohol and anything else on the way up. It just, things are extracted off at different temperatures because they all have different boiling points, and the process, it gets more and more complicated as we make perfumes and alcohols and gasolines and kerosenes and toluenes and other things like that. But fortunately, all we have to worry about is water. So water boils, as we know, at 212 degrees Fahrenheit, and it will vaporize. Of course, it'll start to vaporize, below that. Start to get the bubbles, you start to get a little vapor off. Water is always evaporating, and boiling essentially just speeds up that evaporation. And once it starts boiling, it evaporates, full time. So that's essentially what's happening. So if we have a vessel full of saline water or salt water, or other contaminated water begins to boil, the pure water vapor starts to form. It rises, it gets pulled off of that, and everything else is just left behind. The vapor is directed into it. Well, it can be either a chamber or just a pipe, and I have some images of that here, where it's cooled and then condensed, and then it is collected. The temperatures are maintained at a level enough to vaporize the water. You do not want to over boil the water. You don't want to. There are points at which too much heat can be applied, and you're speeding up the process, and you could be driving off things that are not good for the system. So maintaining a very even keel at as low a temperature as you can get will not only save energy, but it also produces a purer water product because you're not driving other stuff off. The other benefit of those higher temperatures, such as boiling, is that you're going to kill most of the pathogens that are in the water is going to be destroyed by the boiling. So that's a bonus, of course. So essentially, here's a little drawing I was talking about. The solution is contaminated. We'll say it has maybe salt in it. It has bacteria in it, whatever. As it's heated, the vapor, as you're pictured in yellow, is I can't point really that well. It's beyond that. Yeah, it's okay. I can probably, there it is. It's hard to do right there. The vapor's driven off, and this has a thermometer. And I have a little system with a thermometer as well. I mean, it's helpful. It's not absolutely necessary. It's actually very beneficial, really. But the water goes through a condenser where it says cold water in and cold water out. That does not touch the vapor. That actually goes around the vapor, and I will show you with my little lab thing here. That is, if you can see, I don't know if the yeah, there it goes. The coil in the middle is where the vapors are going to go through, and they will come out here. And this thing down here, the inlet, so actually the inlet's here. The inlet's here, and the outlet is here. That lets water pass through the glass part of the chamber that surrounds the coil. So cold water goes in here. By the time it comes out of here, it's warmer, but it's still cool. And the vapors go through that center squiggly thing. By the time they pass through the cooling jacket, they come out as liquid drops here. And I will show you that in a little bit. And that's just a little pictorial. And the distillate, we call it a distillate in chemistry. It's called distillate, but it's just distilled water is going to be collected in another container here. So for the solar aspect of it, this is a typical. If I were to build one, this would be the one I would build, because it really does everything it has to do, and it's not. It's a home. It can be a home built version of what could be a fairly costly thing. But the reason, as I said before, the problem with solar distillation is it's more of a maybe emergency or sort of last ditch effort to get water distilled. There's no other way to do it. It is definitely less expensive. It is also very comparatively a lot slower. It takes more time to do a solar distillation than it does to do a heat-fueled distillation. I don't want to downplay it. I don't want to talk it down. But I think for most people's application, the discussion of not just solar but also the heated fueled versions of vessel distillation is a good combination for discussion. So we can choose what we might want to do. But it's sort of interesting. The salt water, the saline. It says beer and wine there. That's people have experimented with trying to distill fermented materials, but we're not doing that. We're talking about just salt water or brine or whatever. Is in a container at the bottom of the sealed box. And this box is essentially we were talking about something that might be 3 feet wide by maybe 5 feet long from the low end here to the other end, covered in either a glass or acrylic glazing thing, and then the container itself to really make, and that is another problem I have with a inexpensive form of solar distillation, is that to make it inexpensive, that container has to be either plastic or galvanized metal. To do it in copper would be a little costly. Do it in stainless steel would be also costly. You have to buy it, form it, maybe some professional input there, having somebody bend it up for you, whatever. Not absolutely necessary, but possibly. But zinc. If you're using a zinc container to process water, when you heat zinc, it also produces zinc. So not a particularly good thing. Plastic, you really don't know. Not all plastics are food grade plastic, so may be difficult to source a particularly good food grade plastic and form it into the shape you need. You could do it in fiberglass, but again, it's you don't particularly want fiberglass. Fiberglass by itself may not be so bad, but fiberglass and heat isn't a particularly good combination. So essentially, unless this is made out of copper or stainless steel, there are those other inputs that I'm not particularly attracted by. However, this will work if it's built this way. As the vapors rise from the heated water, and the water, of course, is heated by the sunlight that's coming in, they collect on the bottom of that glazing, and just like on your windows at home, they form water droplets, and those water droplets will traverse, because that glass is tilted at a slight angle, 15 degrees or so is that angle, by the way. Not the ideal angle for solar collection, but if it was too much more tilted than that, as I'll show you in the next slide, as I discovered some years ago, we were doing some other types of solar distillation. If the water falls down too fast from that glazing, it may either drop back into the container, which is just recycling it again, which is not, you want to try to collect it, not let it fall back, or it may run down too fast and overflow the collector. At the very bottom of that ramp of glass, there's a little collection trough that goes from side to side, and so that water droplets have no place to go but there's a little dam at the top. It didn't really show that, but it's a little ledge at the very top there. It hits that thing and drips straight down into a collection vessel, which is a little trough at the bottom where it says output, that little box, and then the output pipe, which is pointed out there as output, collects the water. So really, it's not a difficult system at all. However, it is sort of slow, and of course it does depend on the weather. If you have a very hot, bright, sunny day that's going to be blue sky for the whole day, it's going to work. It's going to work fine. If you have periods of clouds come over and maybe cloudy for 3 or 4 hours in the beginning of the day, and then the fog blows off, and you get a good high noon for a few hours, and then it gets rain at the afternoon, it's just not. It's going to function fine. The rain's not going to hurt anything. It's just not going to produce the water that you need. So the process can be limited in how much volume you can get. If you're in a climate or locale that has like in the desert Southwest or some other areas that have a fair amount of good, solid, sunny days all the time, it would be a fine use of that solar collector. The next slide here, this is something we had built when I was employed with Mother Earth News many years ago. We had built this essentially out of a wooden frame. The supply liquid was in the black barrel, and at the bottom of that trough, the corner that's actually touching the ground or near the ground is where the collection took place, and then that little pipe at the top across from right to left or left to right across the top that was the infeed. We distilled water. We distilled the initial purpose was to make a weak beer, a 8 to 10% mash mixture of basically essentially beer without hops in it, to try to see what distillation levels we could get to make ethanol for fuel for use in gasoline engines. It did not. It will distill, but it did not distill nearly to the level, not even close to the level that would be required. And passing it through multiple times didn't really help a whole lot. One of the main problems is at the time we didn't realize, but that angle is, as I said, was pretty good for solar heat collection, but much too steep for proper treatment of the liquid as it came down the surface of that glass on the inside. But I just wanted to show you that this is probably 1981 maybe when this was done, so it's like this is nothing new, and we've been experimenting with this for a while. This is more like it. This particular design here was, I actually grabbed it out of Mother Earth News, a new, much later article in Mother Earth News, and probably 2012 maybe. Another home-built system which has the correct angles. It's a smaller unit, more manageable. You can see by the size of the carboy there, which is essentially what is that, maybe 12 to 14 inches at the base. Maybe it's about 18 inches high. So you can see by that how big the box is. And it does function just fine. You can see the water collecting on the inside of the glass. And again, that glass, by the way, something that small, of that size, you can get away with using just regular cut glass, sheet glass. Ideally, when you get bigger designs, you would want tempered glass, which can get into some money, because tempered glass is much tougher, and tempered glass, when it breaks, doesn't slice you. If you fell on it or something, tempered glass would shatter. Actually, it's a lot tougher. It may not shatter, but if it did shatter, it would break into very small pieces. It would be much less likely to injure or cut you. Plate glass will break into shards and could hurt. But when they're small like this, and if you're aware of the fact that you don't really want to put it in a place where there's danger of people running into it or bumping into it, falling into it, then it's okay. But that gives you an idea of the size of something you could make on a homemade scale. Essentially an aluminum frame there, the glass glazing, and the box itself, which you can make of wood or metal. But if it was made of wood, you could line it with stainless steel or some other aluminum material, whatever, so the wood would not be touching the liquid itself. And you could have a tray in the bottom there that would be something like stainless steel or aluminum to hold the water safely. This is an example of an Indian, a commercial version of a small domestic water distillation system in the country of India. And these are commercially made, and you can see essentially it's the same as the little red one I just showed you, except they're bigger, and there's several more of them. What looks like to be about eight of them here. So these are used to take brackish water in wherever they're installed. They're purchasable, so they could be shipped and applied anywhere you needed. But it basically takes marginal water in places where they may not have the facilities or the income or the resources to do it with more expensive equipment. But it takes marginal water and turns it into potable water. So that's that. Next, I'm going to show you. We're going to leave the solar arena into some of the small household size units that you can actually purchase, the electric units that are countertop type things or under the counter things. You can this essentially has a a water reservoir, an electric heating system that vaporizes the water, and then a fan-cooled system. That number 3 looks like condensing coil, and a fan, which I believe is number 4, blows enough air to cool the condensing coil, so the vapor in the condensing coil gets cooled, and then it turns into the collection chamber, which is number 5 on this diagram. So I just want to point out that in this case, a fan replaces the water that I used in my little system here to turn that vapor into liquid. It doesn't have to be a cold water bath. It can just be a air flow, and that's enough to chill it. So this one here, I don't know, maybe half a gallon an hour or something like that. Let me see. Yeah, half a gallon an hour and a 12-gallon fill. So you fill charge is the fill. You fill it with 12 gallons of water, and it will produce half a gallon of water per hour. So that's, it's a fairly good amount of water. I don't know how much, depending on how much distilled water you need. That's, a reasonable amount of water. So electricity use on that was at about 1,600 watts, which is about what a plug-in space heater would take. A little space heater in your, they'll go anywhere from 1,500 is usually what most of them are, but the low setting might only use 1,250, and 1,500 is the top end. So you're looking at whatever a space heater would take in your house as far as energy consumption. I'm just going to go through this pretty quickly. This is pretty cool. I mean, I just put it in here because I thought it was pretty cool. MIT, the Massachusetts Institute of Technology, in conjunction with some other partners, developed a multi-layer solar still. This is a small one, just because it's a pilot project, a little test. But just to show, it's basically an extremely efficient, internally recycling still that still uses solar to make it work. So it just goes through a stacked series of evaporation and condensing, and then once it goes through it again, and at each level, at each layer, the heat released by the previous layer is used and applied to the next layer. So it's extremely efficient, and I don't know how many plates are in there, but there's a number of plates in there, and they will just process that water and heat it and condense it and heat it and condense it. And the overall efficiency of this, it is claimed, by this research model, it's totally laboratory research, is 385% in converting the energy of sunlight going into it into the energy of water evaporation. So that's that's quite a thing. It's not available commercially at this point at all, but it's nice to know that people are working on ways to convert our marginal water into potable water. Chemicals and volatile organic compounds. And this is where it gets a little bit tricky. Most of the stuff that we would consider toxic and not beneficial to have in the water, including pesticides, whatever, they boil at a significantly higher temperature than water. So they will remain in the container. When the water boils off, we extract the water and process it and use it. But the bad stuff is going to stay in the vessel. So, by and large, almost everything that is considered not beneficial and pathogenic and bad is going to stay in the vessel. So essentially that, except there are some parameters. Before I get to that, the boiling process, as I mentioned before, destroys the majority of the biological contaminants in the water, just because the water reaches a temperature of boiling and it kills them. So that's a good thing. However, certain volatile organic compounds, we call VOCs, which the common ones would include toluene and benzene and chlorine, actually have a lower boiling point than the water does, so they will be vaporized right along with the water. So that's something to be aware of. So any water distillation system that you might see for sale that claims, without filtration, that claims to guarantee 100% pure water coming out the spout is actually not being completely honest, because if there happens to be a toluene or a benzene or chlorine in the water, so if you took your tap water, which is chlorinated from the city water tap, and put it through the home distiller, it's still not going to remove the chlorine, because the chlorine boils off at a lower temperature. So on our way up from 65 degrees out of the tap up to 100 and 150, 175, where it's going to start to vaporize a little bit, and then on up to 212, that chlorine is going to, and the benzene and anything else that might be in there, is going to vaporize and get processed and extracted right along with the pure water. So the water isn't pure. As I said before, the way we handle that is to pass it through then a charcoal, activated charcoal filter, which will strip out the rest of that, rest of those harmful materials. So to cap off then, distillation, and in conjunction with the activated carbon or charcoal filtration, will remove both the biological contaminants, any sediment and metals that are left behind in the process. And then when you combine distillation with that and the active charcoal filtration, it will provide water which, as I said, is 98% plus free of any impurities. So we're removing the things you might want to concern yourself about, why you might even approach the idea of making your own distilled water. We're removing arsenic, removing asbestos, removing benzene, fluoride, chlorine, mercury, lead, any nitrates, radium, and radon. So all the big ones are coming out. So there you go, and that's that's worth worth the investment. Again, filtration, compounded filtration will do similar things, but we're really talking here about distillation, so I wanted to make it clear. However, again, we're with this list here I presented, that is a combination of both activated charcoal filtration and the distillation. So you will, if you don't use the filtration, you'll remove the fluoride, but you may not remove the chlorine if you have chlorine in your water. So something to think about. So to cap it up, as far as the distilled water, we're going to destroy bacteria, viruses, and microbes. We're going to remove any soluble minerals that have been collected in the ground, passing on its way to becoming groundwater. As it collects its minerals, we're going to remove those soluble minerals. We're going to remove fluoride. We're going to remove inorganic materials, the heavier organics, and any heavy metals that are in there, like the zinc and the mercury and anything like that. It does soften the water a little bit. It does not remove chlorine, as I said earlier, and it does not remove the volatile organic compounds, which by the way, if you're in any normal rural environment with a well, or definitely if you're on city or municipal water, you shouldn't have any VOCs in there anyway. The only concern I might point out there is that if you happen to be near a chemical plant or a processing plant, or a place where they may be using in their production facility, cleaning or processing or manufacturing, they may be using volatile organic compounds, like for cleaning agents or whatever, and there's any possibility it might have gotten into the water supply, then this would apply. However, as I said before, if you get your water tested, you'll know if your water supply might be contaminated. So that's like really the first step, is to get it tested. So distilled water can also have a low pH or be slightly acidic. So that's not a bad thing. There's a range. The potential hydrogen. The pH of water runs from 0, which is highly acidic, to 14, which is highly alkaline. And we're looking, the middle, of course, is 7, and we're looking at water. People drink water in the range of, into the 6, the 6 up to, over 7, 7.8, whatever. So, we're in that little middle range here, and it really just depends on a matter of taste. So the solar still, to get back to the solar still, because I know that's really sort of what started this whole webinar conversation. Just to give you an idea of what you might be looking at, 1,000 square inches or 7 square feet. 7 square feet would be what? Would be 3 by, or 2.5 by 3. Would that be about right? 7 square feet of glazing surface will produce about a gallon of pure water a day in a typical environment. So a properly designed 4 by 8, that would be the size of a piece of plywood, a sheet of plywood, 32 square feet, would yield somewhere between 2 and 4 gallons per day, again, depending on your solar input. If you have a completely bright, sunny day if your solar window is like 12.5 hours early in the morning and there's no clouds, no mist, no whatever, and you're going all the way well past 6 o'clock, you're going to be looking at closer to your 4 gallons a day figure. If it's not that, if it's just a good solid middle of the day solar window of maybe 5.5, 6 hours of good sun, you then be down into the 2-hour gallons per day. A gallon, 2 gallons per day doesn't sound like a whole lot, but when you're talking about drinking water or just just a little bit of water for a special purpose, it's perfectly adequate. So a single container, a single basin distiller, solar distiller, will be able to produce a full 4 gallons of a day, with lower expectations if clouds come over or if you have just a marginal day. 32 square feet, as I said, is a size of a sheet of plywood. It's 4,600 plus square inches, as opposed to the 1,000 square inches of the smaller one, which I'm saying would make about a gallon of water a day. So, and less than a gallon of water per day if we had deteriorating solar conditions. So just a little reference. So the economics of solar, and just some comparison. It's cheap. It's not, once you've built the system, it's not expensive to distill. So we've got, even if you purchase a commercial distillation unit, or you build one to almost to the level of a good commercial system that produces safe drinking water with a basin that has maybe copper or stainless steel in it, you're looking at about 7 to 10 cents a gallon of water production, cost of water production. You have to, if you're trying to do a return on investment kind of thing, you'd look at the cost of the manufacturer's unit, and then also the life cycle. There's really not a whole lot that's going to wear out in a system like this. I mean, a commercial system, what's going to, unless you break the glass or whatever. I mean, if you keep it clean, it's really, it's the life expectancy will be quite, they would probably give you something like a 10-year window, but it'll go well beyond that. Now, we looked at a little electric distiller before, the tabletop one, the countertop one. That will produce water at a price of about 40 cents a gallon, depending on the cost of electricity of your local power company. Now, we measure that by kilowatt hours. Around here, I think we're running at 12.7, something like that, kilowatt hours, 12.7 cents per kilowatt hour. So the machine will use, typically something of that size would use about 3.2 kilowatt hours per gallon of water. So you can get an idea, do your own calculations. But so you're looking at a price of maybe 4 times more expensive to do it by plugging it in than you are to do it by using the sun. And to compare it to, I should have put up some of the costs for gas too, but on a propane or natural gas stove, the prices are comparable. Propane's going to be a little more expensive maybe, but they're going to be in the range of the electric one. The other option, on especially the system that I have in the little videos I have, another option is just a wood fire. You just put it on top of a wood fire with a grate or a charcoal fire, and you can do it, a lot cheaper. Not quite as cheap as solar because you have to, buy, harvest the wood somehow or whatever. But it could be, if you have free firewood, quote unquote, if you cut it yourself and you don't really count yourself as paying yourself to cut it, you could basically make distilled water all day long for next to nothing. So little price parameters there. Maintenance, again, the distiller is going to eventually collect the fallout of the sediment from the water that's in the introduced into it. There's going to be minerals in that water. So and they will stay behind. So periodically, just a good cleaning with white vinegar. Apple cider vinegar is not. White vinegar is better for it because it's not doesn't have the sweetness of it. It's just a pure vinegar. We just use a vinegar solution to maybe half and half, 50%, to remove any scale on a regular basis. Obviously, the mineral content of the water you're putting into it is going to dictate how often it has to be cleaned. If you've got a heavy mineral content in your water, you're going to have to do it, on a more frequent cleaning. It might have to be once a week. If it's typical, average mineral content from well water, it may be maybe every 2 weeks, or possibly even longer, up to a month maybe. The filters that you're putting it through afterwards, which I unless you need just distilled, well, it depends. But if I'm doing it, I put it into a pitcher type filter, which has its carbon filter built in. So you put your distilled water into the pitcher and then let it filter through the carbon, and then you have your absolutely filtered and distilled water. So the filter itself, the retail filter you might buy at the home improvement store or the hardware store or whatever, can last up to 1,000 gallons. There are filters that let me see. I don't know if I have that other one there. There are filters that are what I call proprietary filters. So when you buy a is it Alexis or Berkey or one of those? There's at least half a dozen manufacturers of high quality stainless steel water filtration devices. When you buy one of their filters, they're generally compounded filters, and they will last. They're bigger and they will last longer. So you're looking at maybe 3,000 gallons of process before you have to change the filter. There are additional fluoride filters that are in some of those systems that are available and added in, and they need to be replaced on a more frequent schedule because they're they'd be water. If you're not distilling it, if you're just using the pure filtration without distillation, it's going to task the filter at a much higher level, and it's going to have to be replaced at 1,000 gallon intervals at least. So we have that. I don't know. I was gonna it's not really necessary. I think the pictures may show it, but those other filters are bigger. So as opposed to the little pitcher filters, so they do last longer. So now we're going to look at some of the processes, or how the process of actually works in the kitchen. So I'm going to just show you the little. This is not the water that we're going to be drinking. This is the processed water. I want to show you here the little pump. This is a in that bucket, in that blue bucket, it's just a little submersible pump, which is sort of like an aquarium pump. It's a 110 volt, and it sucks in the water from the bottom of itself here at the very bottom, and then it pumps it out through a tube at the top. So you'll see that's underneath that. I actually put ice in there because I really wanted it to be very cool when I was trying out this filtration, this distillation. So this black unit is underneath that ice there, and you can see the tube coming out. So I'm just showing this first. Oh, there's the filter there at the little corner there in the lower left-hand corner, sitting in the water. This is filled with water, and then I just put some ice in it to make sure the water is going to stay, really chilled. The pump is what's passing the water through the coil, which you can probably barely see. That the blue bucket is actually behind this stainless steel pitcher or stainless steel vessel, and you can see the tube in the very. Let me see if I can get it up there. And on the left-hand side of the picture there, at the very top, there you can see the edge of the tube coming out there. So the water, the vapor water is coming up through the lid there at this larger round lid where the thermometer is in. That's the thermometer. This is the lid here. The tube that the vapor is coming from this vessel here, going up through the tube, up through here, and then going into the chilling vessel, and where the water jacket is chilling it. And then it comes out that little, on the extreme left side there of your image, that little stump of a white tube is where I've been collecting the water out of. So I put a little vessel under that, and essentially this is maybe almost a 10-gallon vessel. So fill it with water. I got the thermometer right in there. That lid gets sealed. There's a sealing ring underneath the lid there, and it gets put down right on top of that vessel. And then you can see the clamps right and left, and there's one in the front and one in the back, which you cannot see. But the lid gets put down tight, and a small amount of pressure is built up when it boils, which allows the vapors to pass through the trying to see where I was before. Anyway, behind the thermometer, there's that tube, and that essentially would be the same as that. So the vapor would be coming up through the tube and coming out that little white extension there, which I showed you in the image. And this is an important thing that I want to mention here. This is a pressure relief valve that they use in pressure cookers. It's just a safety valve. So if there's too much pressure, I'll just take it out and show it. It's only a little teeny thing, and it's easily I don't know this one here yet. It's easily mounted by drilling a hole. It's very small. You can see that it has a hole in the bottom, and a screw mount. So you unscrew the screw, put it through. You drill a hole in the lid and screw the screw back up. It has two seals that go with it. So essentially, that fits into the lid of the vessel. Back to our image of the boiling pot. There, and the reason this is because when water actually turns to steam, it expands tremendously. And since we're controlling the heat, I'm not just flipping it up and walking away for 15 minutes. I'm actively watching the thermometer crawl up from 60 to 100 and on up to, when it gets to about 170, I keep my eye on it a lot more diligently. But when it turns to steam, it flashes and expands significantly. So in the event, this tube that I showed you before is only a small, it's only a quarter of an inch or maybe 3/8 of an inch in diameter. So it's plenty enough to let the steam out. But if it were to expand, violently, it could pop the seals on the lid or possibly break the clamps on there. I mean, that would be if you turned it up to full tilt and just ignored it. It may blow off, and I'm not saying an explosion like a boiler exploding, but it may break the seal in the lid. And if you were sitting there watching, waiting for it to wondering why it's not getting temperature or whatever, you don't want to be scalded by that. That is not supposed to happen. It shouldn't happen, and there's no reason why it would happen. But just to, if you're careful, but just to make sure it doesn't happen, that little pressure valve is there to release any significant pressure before it ever becomes a problem. So that's essentially that's a safety thing I want to add in this, because some of these you're going to be making these from cooking pots or whatever, or purchasing this online. These are available online, from our normal online outlets, either stores or our big shopping outlets, our eBays and our Amazons and all that. And some of them will not come with that unit. I would suggest you buy one of those pressure cooker relief vents and install it yourself in there if it doesn't already have one, just for safety's sake. Let me see what we got. Now that is an example of a water purifier, a commercial water purifier that many people use just to make sure that they have that their tap water is filtered properly, and they're removing just every bit of possible contaminants they can possibly remove with with a additional process. Those things, many different manufacturers make them. We've heard the names of Berkey and the Alexis or Alex Pure or something like that. There's at least 3 or 4 other ones, and I'll show you the insides of it in a minute in the pictures. But they're costly. I mean, they can go from from $200 up to well over $400, depending on the size. This particular one I got at new in the box. Somebody had either got it as a gift or got it and it was too big or whatever. But at the thrift store, I think I paid $40 for the whole thing, and hadn't been opened. So I lucked out. But if you want pure water without distillation, this is a good route to go. I'm just throwing that out there. Again, the brand does not make a whole lot of difference in my mind. I mean, the filters all seem to be about the same. They have different choices, different options, and different. They go by different multiples. In other words, that's the size of the filter. It's about the size of a small beverage soda bottle, of a 12-ounce or something like that, a 16-ounce bottle. Those holes in the bottom of the vessel. There's a large vessel on top and another collection vessel at the bottom. One nests inside the other, and you can put up to 4 filters in the system, which of course the more filters you put in, the longer that they will last. And then if you don't have the 4 filters, they give you these plugs. Those little black dots are plugs to plug the holes up with, so the water doesn't just go through the holes. So the filters are designed to let water in through the sides, and then it goes through the filter, and gets filtered, and then goes into the collection vessel at the bottom. That's the size of. There's my hand. That's the size of the filter itself, and the little plug at the bottom is where it plugs into the bottom of the processing vessel, and it's sealed. And then as the water is processed, it goes through that little nipple and goes into the receiving vessel, or the reservoir. And let me see what that is. Let me see if I can even. Let me go back to look at that. And it's collected at the bottom. I'm trying to even figure out. That's actually another shot of the. That's a reflection. That's why it looks so funny. That's another shot of the filter in its container. This goes to show how clean and shiny it all is. It makes it look like there's a curved thing in there, but that's really just a reflection of something else behind it. That's the filter. That's the home improvement pitcher type filter that I used, that I showed you before. That's the copper condensing coil that I showed you earlier. That's an image of the thermometer on the unit, and I think I said before it's not absolutely necessary, but I think it's I think it's good to have because you really don't know what to expect unless you have done it before, and you don't know what happens when you do it unless you have a thermometer to see what happens at certain temperatures. So any of these commercial units you buy online are going to have the thermometer. They should have a thermometer included with it. If not, you can drill a hole in the top of the vessel and buy a sealable stem thermometer. They come in stem lengths of 2 to 4 inches is all you need for that. And put it back in. They have to be sealed into the lid with the 2 grommet seals they provide with it. This is the image of actually inside the condensing unit itself. The top unit on that machine, on the distilling machine I showed you earlier, the vapors are coming in through the top there, through that silver pipe at the top, coming from the lid of the distiller, and they go through the copper coil where they're chilled, and then they pass out through the stem at the bottom, which you can sort of barely see there, but that's that. Probably not as good a picture as I could have taken. So that's the whole thing closer up. I can identify the parts there. The vessel itself, right there at my shoulder, with oh yeah, I can. Can I do that? Yeah, I can do it. No, it's not showing up on it.
It was there. It's gone now.
I'm sorry. Just
move it to the right or the left, like on the other
oh,
side.
there it is. Okay, I'm off to the. I'm not really sure you can. Oh, there it is. Okay, so there's your boiling vessel, where your raw water is going to go into, and then clamped on top is the lid with the thermometer in it, and ideally on the other side this little pressure valve release there, just a small little dime-sized thing. Resting on top of that, it's not mounted on there, it just sort of sets on there, is the condensing vessel with the steam outlet coming through that copper pipe behind the smaller vessel. You see the copper pipe coming out of the lid of the big one, goes through the silver pipe and into the coil, and then the water, the distilled water comes out that little looks about an inch-and-a-half nozzle there at the lower or the middle on the left side of the image, and that other tube, the white tube that's sort of curved there, that's the cooling water tube. The pump is feeding that into the bucket, into the cooling bucket, and then the cooling bucket's draining it back down into the back into the blue bucket. So let me see if we got a good, and there's basically your image of your in process. I just opened the lid a little bit to show, it's boiling, your vapors are coming off, your thermometer's up there. It's not quite at boiling because it's sort of out in the air. When it gets sealed up, it will come to boiling. But it gives you an idea. It doesn't have to be violent. I turned this up a little bit to show you how, to show you that it actually works like that. I don't know why we're not. Finish. Okay, let me get you going again. Didn't repeat. When it is operating, you'll put the lid on, of course, and clamp those clamps. I think in this case, I only add a little bit of water. It's only an inch or so at the bottom, just to give you an idea of more steam and less water. It does not have to be filled to the top at all. In fact, it works better if it's not filled right up to the top. It's halfway of a fill is just fine. So I want to show you the. Let me see if this is. Yeah, that's just a. I think probably a very similar image of what I had before. Just to give you an idea of the scale of it. It's my stovetop, and it'll take every bit of the big eye. I mean, it's a 13-inch vessel at the bottom. I think it's about 13 inches, 13 or 13 and a half at the bottom, and I think it's 13 and a half tall. So it's up to that's the big one, and then the little one is something like 7 inches by 5 inches. So you get an idea of scale that way. I don't know if that's, I'm not sure why. That's just pretty much the same thing. I think it was just a different image of what I showed before. And that's the, that's the scale of the on top of the stove.
I think it's a video.
You want to go back to the video?
No, this is a video.
Oh, it is a video. Okay. Yeah. Oh, yeah, you're right. Yeah. I just didn't put it on automatic. No way I'm not. Is that? Oh, there it goes. Yeah. Yeah. Now, what I wanted to do, this seems to be stalling here. Yeah. So ideally, it's going to come out in spurts, and that's a sign of it actually working. It passes a little bit out, and then it catches up with itself and spits a little bit out. That means your temperature is at about the right level. If you turn it up too high, it's going to come out in more of a stream, which we're going to show you in a second. But I just wanted to show you what it looks like correctly. You can see the condensation forming on the condensation vessel there. That's how high the water is at that at that level. I don't know why that isn't. Oh, it's finished. That's why. The reason you don't want to turn it up too much and let it flow. Let me show you the next one where I think it's going to be more. I think that's the correct one. One of them I had. It's like a real constant flow, and that's an indication of the heat being too high. And the danger of that is it's really nice to think that you're going to get more collected water that way when it flows more constantly. But what you're doing when you turn the heat up too high is you're potentially driving out some of those contaminants that may be activated at a higher temperature, which you do not want to do. You want to maintain that as close to 212 as you can to make sure it's only water you're driving out, with the exception of, as I said, the toluene, the benzene that may or may not be in that water, but that will boil out, that will come out anyway at a lower temperature, and so you can't help that. But you don't want to encourage to drive out stuff that might vaporize at a higher temperature. So you start cranking that heat up, you're gonna start driving out things that you don't want driven out. So that's one, perfectly good reason to have a thermometer on there. Let me see if I have a better image. Yeah, I think this one is probably a better example of what not to do, because that water, as you see, is coming out in a more steady stream. Now, if your thermometer is accurate, and you're watching it, and you're running that thing at very close to 212, if it's doing that, then it's probably okay, because it's just working. I mean, it's not being overheated. But this really just gives you an idea of the rate of flow that you can expect with, a stovetop distiller. You're not collecting a ton of water, but it builds up after, over time, and it just depends on how much you need. But something you might do once a week or whatever, and collect your water and put it in clean containers, and you've got your distilled water. I mean, I use it more for filling batteries and sticking it in my leaky radiator in the car than I am for anything else. But if you need to be consuming it, drinking it, or using it for irons or hair shampoos or whatever, you still make plenty of it. So I think that's. Let me see. Was that? No, that's the end of the show. Okay. I think I just wanted to continue a showing of the rate at which you could do it. But that's essentially about the end of the conversation. I mean, I think for a little bit of investment, you get your own distilled water. It's not like it's expensive in the store, but I have a car that has a leak in the cooling system, and it's a very small leak, but I do have to put water in it every week at least, and maybe every couple of days, just because I just don't want to go to the expense of removing a cylinder head to fix the gasket. So I just keep it filled with water, and you go to the store and you get a dollar's worth or $1.29's worth gallon of distilled water, and really you can make it yourself. You don't need to worry about the purchasing it. So there's nothing they're doing to it that you can't do yourself. So I don't know what our time looks like, but no, I essentially said this is going to be a little bit of a shorter webinar, and we're running about an hour and 20 minutes. So that's that's about it. So that's that's about it. If there's any comments or anything or questions, I'd be glad to take them from the webinar people. But so far we're there.
All right. Give us 1 sec. All right, we're going to start answering questions now.
Oh, you have some questions? Sure. Yeah, we got some questions coming now, so which I hope I can answer them.
All right. Ooh. And I actually just need to make sure that the screen doesn't lock, because it'll just lock every minute if I don't. Oh no, I'll just unlock it again if it locks.
Okay. Medically, can I use the water that comes from my A coil and from my air? Oh, okay. Can I use the water that comes from my air conditioning and condensing unit from the air conditioning? Is it supposed to be distilled water? No, I wouldn't. I would filter it if I were to use it. I think it's going through tubing and piping that you really don't know what is. That's not food grade piping. So you really don't know what that is. If you were not going to consume it, if you're using it for for washing your hair or using it for your car or whatever, so it'd be a lot safer. But without really knowing what the material was that was passing through the air conditioning system, it's not really as pure as you might think it is. Okay, so that's that. Next question would be, hi folks at Living Web Farms, is it true that distillation can extract fallout radiation in the water? It will extract radon, but I don't claim to be an expert, but I mean, just for the little expertise I have in that radiation, the other types of radiation that we're exposed to, either in the environment or from our power facilities or anything else in the air, are not. It's not the same. It's a different type of than radon is. So I would say no would be the safest answer for that. If it can take out radon, it may be able to take out other levels, but I wouldn't go any further than that on it. What will take out iron is the next question. What will take out iron? Would distilled water be for that situation? It will, it'll remove, with the filtration, it will remove the iron. And that's, iron, the ion exchange and the reverse osmosis were designed to remove that and, a lot of the other things like the calcium and magnesium. But the distillation is, not, it's going to settle in the container, so it will remove some particulate matter from it, but it's not going to. I don't know if it's going to take it completely out, so that's why I would pass it through a secondary filter before trusting that all the iron's gone. Iron in the water, by the way, is not a crisis. We need to have some amount of iron in the body, obviously, and as I said, you get it from food anyway. The excess iron, if it's staining the sinks and doing that, it may not always be iron. It could be some of the other calcium and magnesium, and there's another compound, another mineral that does the staining as well. But it could be that, and not the culprit may not be the iron. If you have hard water and your calcium and magnesium is a problem, iron is a very small percentage of that problem. It's going to be there, but compared to the other two, it's not as much of a problem. So, in the answer to that question from Tracy, I would just say that I would back it up with an activated carbon filter, and you'll be fine. Let's see, we have another question or comment. I was told that the condensate from your air conditioner picks up pollutants that would sit on the outside of the coil, but I don't know. That makes perfect sense to me. Pollen, there's going to be all sorts of stuff that is gathered. I mean, insects, and there's just stuff that's on the outside there. If it has to pass along or through before it drips out, it's going to be contaminated. There's no question about it. So it may be organic contaminants, but still maybe not something you want to drink. Another viewer says that my concern with distillation is the quality of metal used, because 0 parts per million water will pick up toxic metals like nickel from most stainless steel, probably to a small degree, and not really sure. I think basically what you're saying is that the absolutely pure water is a magnet for it seeks other minerals. It seeks minerals to bond with, and that's true. And that's why I said early on in some of the dental reports, people who might drink pure water or distilled water exclusively, who maybe that's all they would drink, would possibly be risking minerals being removed, necessary minerals being removed from bone and teeth, and that's been a discussion in the dental community. So that is not untrue, and it's not untrue that what this fellow says, that it's actually a magnet for it's seeking minerals and it wants to take it from metals it touches. That's true, but stainless steel, good quality food grade stainless steel is produced to it's called 304, 308, and 316 is the numbers in those types of food grade stainless. It's going to be processed to a point where it's not really drawing out enough to be an issue. So that's be the comment on that. Are we? The phone. What happened here? It went off. Let's see if there's more questions. I don't know.
Can you touch on how we can restructure the water?
Let me see. Reverse osmosis. This is the same commenter. He says reverse osmosis. I worry about bacteria growing in the tank or filters. I've heard of people using RO first and distilling that. Well, yeah, if you don't clean the RO filters, I'm not a big fan of like that kind of investment. I would look at where my water is coming from and why it's getting to the point where you need to buy that kind of equipment to process it. But in many cases, it is necessary. Once you buy it, you have to maintain it. And the problem with the RO filters, other than the fact that it discards more water than it actually delivers, which is just the nature of the process, other than that fact, it does have to be maintained. And there's nothing wrong with that. You know that going in. If you don't maintain it, it's on you. So that's what happens. If you don't maintain it, you do have buildup, and that's your fault. You can distill after you've gone through the RO units, but it just makes more sense to me to keep the reverse osmosis unit clean and maintained, so you don't have to worry about it. That's just my take on it. Let me see. Another comment saying forced air. This is more on the air conditioning. Forced air blows dirty air across the coil, but does it wash into the water from the coil would be the question. Again, we sort of already addressed that as it comes out, it's going to touch other things, and those other things are not going to be pristine. So, there's that. I guess collecting water from your air conditioning system is a noble thing, but I would use that water to wash my car or something. It's not water that you have to make potable. You can process your better water to make it absolutely 98+% pure potable water through the distillation and filtration that I was just talking about. See, RO can harm some membranes in the digestive system. I'm not knowledgeable enough in that area that'd be something I would be interested to look into, I guess, but I don't know. I mean, I can't, it's really removing cysts and bacteria and small particulate. A lot of that's a very minuscule particulate matter removal. And I'm just not really sure what, the only thing I can think of is maybe, just as distilled water does, people suggest that because it's absolutely pure, it's removing minerals that your body might need. But as I said earlier, you're getting the lion's share of those minerals from your food and supplement intake, not from the water you drink. You certainly are getting it from the water, but majority percentage comes from your food. So that's that. We're talking about chlorine in the water. I'm not really sure, but is it proven that chlorine stunted growth is null if soluble nutrients are added? So I guess the suggestion is the chlorine stunts growth, and if you supplement the chlorinated water with other nutrients, that it's going to remediate that problem. It just as a test is in order. I don't consider myself knowledgeable enough to answer that properly. Really, again, it's a very good question, but it's not not on me. I don't consider myself that knowledgeable in that particular area. Are zero water filters ion exchange? I don't know. I assume that Zero Water Filter is a brand, but I don't know enough about that. Would it be possible to boil off the toluene, benzene, and chlorine at lower temps and then hook up to the condenser? Well, essentially, yeah. I mean, that is what distillation is all about. I didn't want to get into the discussion of distilling. I certainly didn't want to bring in distilling. We're not here to talk about the distillation of spirits or other distillation other than or petroleum or perfumes or anything else, chemicals or anything like that. We're just really talking about the water. But the equipment that we use to distill the water is essentially with various layers and levels and design changes, is the same kind of equipment that they use to distill liquid chemicals and ethanol and anything else. So yes, that's how it works. I mean, they pull it off, they condense it at the temperature at which it condenses. And at the next level, they pull off something else at the temperature that it condenses. And as the temperature rises up, they pull it off at that level. And so there's a column, and on the way up the column, as the temperatures change, they pull off what they need. And chemists have established over the centuries that what comes off at what point. So that's what fractional distillation is all about. Can you use a dehumidifier? I assume you mean, can you use a dehumidifier to make your water and then distill that? Yeah, you can. Again, if I was going to do that, ideally, if I was going to use the water from the dehumidifier, I wouldn't process it. I mean, I would use it to wash dishes maybe, or rinse dishes, or wash my car, or clean something. But if you were talking about if you had to use it to drink, I mean, I would then distill it after it went through the dehumidifier, because it's gone through particulate in the air, it's gone through the surface of the dehumidifier itself. The filter on the dehumidifier is probably filthy. All this on and on. So once you've collected the water out of the dehumidifier, which by the way is significant. I mean, those things you've got quarts of it. If you ever picked the tub up, they're heavy. I mean, a gallon or a couple gallons of water there in the bigger ones. So it's not an insignificant waste of water if you just dump it down the drain. I would consider putting that through distillation process and then filtering it through a simple activated carbon filter, and then you're good to go. it looks like the end of the questions from the online folks. So really, I think it's a good, good class. An hour and a half of discussion. It's something this size. It's difficult to bring it into the studio and show you in person, so I had to do the videos. But you can do further research and look online for any potential purchasable stuff, or you could make out of your own kitchen utensils. Seal a pot and make the boiler thing, and you can easily make a condensing pot out of a smaller unit. And you can find not just online, not just through your online merchandising people, but the brewing supplies. It's a big venue, has grown significantly in the past 10 years or so. Brewing supplies, people who sell brewing supplies for beer makers, they have a lot of this stuff already made if you want to buy it in various sizes at different cost levels, and all food grade stuff. So it's not just huge microbrewery type sizes, but down into the little home brew kind of things, and they sell quite a few. There's at least, I order parts from them a lot, and there's 2 or 3 or 4 that I order from all the time, and there are probably a good dozen out there that are perfectly capable of selling you and good equipment and able to answer questions you might have on the equipment. So that's another idea. But anyway, I'm pleased to have made the presentation, and hope everybody got the answers they needed and was happy with the discussion. And we'll see you next month with our next online webinar series for the month of August. Thank you. So the steam comes up from the kettle in here, goes through the pipe, and rotates through this condenser, and then exits out the spout there. And meanwhile, the water is coming into here, or comes into this one and fills this small container, and then comes out of that one. And the coolness of the water is what condenses the vapor in the coil.